Alright, so the last part of chapter 23 has to do with RC circuits. These are circuits that contain both resistors, like a light bulb or maybe a speaker, as well as capacitors. And these kinds of circuits are typically used as time delay circuits. And so what we see is that there's usually like a battery of some sort that's charging a capacitor. And so over time, this battery is pumping energy into this capacitor until the capacitor reaches its capacitance, at which point it is full. The switch flips over to complete this next circuit, and capacitors, unlike batteries, discharge very quickly, and so there's a rush of current to that resistor, and then the capacitor is discharged, leading it back here to be charged up over time by the battery. And so what we see are these periodical kind of discharges to that resistor. And this is a great example of like a blinker or a windshield wiper in a car. The battery charges up the capacitor, and then it flips over and discharges very quickly to whatever the resistor on that circuit is. What we see is that as a capacitor is charged, the voltage increases exponentially on that capacitor. And so it charges up very, very quickly, and then it reaches its threshold or the EMF of that battery, at which point it charges a little bit slower, and then the current decreases exponentially. And so as a function of the time constant, voltage goes up very, very quickly, while current decreases very, very quickly. Right? And so, like I said, this is just a matter of this kind of switching back and forth between these two circuits. Ultimately, the only reason that I want you to know this is because every nerve cell in your body does this. It's a lot like an RC circuit. It kind of increases its capacitance, and then it lets go and flips that current onto the next part of the cell. If I were to cut a nerve cell in half, it would look a lot like this. And typically what we see is that there's a conducting fluid inside the cell. Remember, salt water is very conducty. And there's an outside conducting fluid. And then there's this cell membrane, which is a lot like a capacitor. Right? And so this looks like a parallel plate capacitor, where the electric field is running from positive to negative, right? And if I were to just maybe take a slice of this, well, that's what it looks like. And so the electric field is pointing inward towards the inside of the cell. And what effect does this have on the cell membrane? Well, it kind of polarizes the whole thing. And so what we see is that it has this RC circuit kind of effect, that there's a resistance in that membrane, and there's kind of a potential on either side of it. And so electricity in the nervous system, the whole way that your body sends signals this way, is typically you have a resting potential of negative 70 millivolts on that membrane. And then once there's a stimulus, there is kind of this rush of sodium ions into the cell. And so there's some kind of a stimulus either from another part of the nerve or maybe across the synapse. There's this chemical stimulus, and sodium ions begin to rush in and polarize that membrane. And what we see very quickly is that membrane electric potential rising to about positive 40 millivolts, and that's about as much as it can handle, at which point potassium ions begin to shoot out of the cell and repolarize the cell back to its resting potential. But cells always overshoot this, and so they put out more potassium. And this is a little overshoot, reestablishing the resting potential. And this is just a simple diffusion of ions to return that cell to its natural state. And so what we see is that sodium channels open, sodium ions flood in, potassium channels then open, allowing potassium to flow out, and the potential, this little yellow bar, kind of moves down the cell in that direction. And because of those voltage-gated ion channels, they respond to that stimulus to charge and discharge, much like an RC circuit. So that capacitor gets built up, and then it discharges and lets those those potassium ions back out, establishing that resting potential. However, if this is all that happened in a cell, is really inefficient, because think about the sheer distance from your brain to your big toe. It would take about a second, right? Or maybe even closer to 2 seconds, if you're tall, 2 meters, um, to get that thought from your brain to an action of bending your big toe. And so in terms of a body and our ability to survive, this basic speed of transmission, a meter per second, is not good enough. And so the body's solution to this is the myelin sheath. The myelin sheath is this big, you can think of it as an insulator or a non-conductor. Um, and what this does is it allows this whole charging and discharging to jump distances. Because, well, this is so big and thick, and it's not a good conductor, that electric potential can't really get built up across it. And so nerve cells have these big insulators, big sections of insulation, so that once one of these things charges up and sends the signal on, well, it actually kind of sends that signal all the way through to this next node of Ranvier, where it can be charged up again. And so what this does is this kind of fast circuits, right, the current traveling through that nerve cell, and allows it to jump from place to place instead of having to also build up that potential in this area. And so it allows it to build up, build up, build up, and then zap right across to that next node where it builds up, builds up, builds up. And this gives the body a much greater speed of transmission, and then obviously a much better reaction time for that fight or flight mechanism in animals, right? Um, this whole process of that electrical kind of capacitance and RC circuit current jumping from one place to another is called saltatory conduction, and it is specialized in nerve cells. However, there are a few neurodegenerative disorders, and neuro being neural pathways, some neurons, and then degenerative breaking down disorders, where this gets disrupted and kind of eaten away by the body's immune system. And what this does is as that gets eaten away, it slows down those neural times again. So a good healthy neural time with good myelin sheath is 25 meters per second, and that makes a lot more sense for our reaction times. But as those get kind of broken down, either with age or autoimmune disorders, it can lead to a whole host of side effects, most of which include effects with vision, or maybe you see heat sensitivity, speech impairment, of like, I'm trying to tell my body to do this thing, but it's not doing this thing because, well, my neural pathways aren't acting correctly. And then even in some cases, we see difficulty coordinating your movement, or even controlling bowel movements and urination and stuff like this. Those neural pathways get broken down, right? And so I'm actually not going to assign any homework for this section. It's all going to be conceptual. And I will see you guys tomorrow in class with your quiz completed.